Okay, hello and welcome to lecture 13 on medium access control. So we're getting into the chapter on the link layer. But last time we wrapped up on the control plane of the routing layer. We talked about IP Anycast, which was a BGP trick to send traffic for one IP address to more than two machines or more than two locations in the network, kind of giving the creating an IP-based load balancer in a sense. We talked about broadcasting and multicasting as alternatives to unicast. In other words, so far in the class we talked a lot about sending messages to one machine. Broadcasting is the idea that we have a message we want to send to a lot of machines, a lot of hosts, every host. Multicast is a machine you want to send to many hosts, but not all of them necessarily. And we talked about a couple of ways to implement broadcasting. Broadcasting is an important primitive in networking. It's not implemented on the internet per se, because you don't want to send a message to everyone, but multicast is kind of implemented in certain parts of the internet, although not widely. To do broadcasting, I talked about two different ways to do it. Controlled flooding involved, it was a distributed way to do that, where you had a sequence number on your messages as well as the information you're trying to transmit, and you would propagate it if you had not received that sequence number and message combination before. An alternative was to create a spanning tree on the network, which required information about the whole network. And you can just transmit the information along the edges of the spanning tree, which is a more optimal way of doing it, a more efficient way to do it. But it requires more information, central information about the whole network to determine that spanning tree and to share the spanning tree with everyone. To build a spanning tree, we showed that Dijkstra's algorithm can construct a minimum cost spanning tree in terms of the summation of the edges. Dijkstra's algorithm can be used to construct a different kind of spanning tree starting at a node where you're getting the shortest path to everywhere else in the network. So if your edge costs represent latencies, you can use Dijkstra's algorithm to get the quickest broadcast. If your edge costs represent something that's cumulative, like money or energy, you can use Prim's algorithm or Kruskal's algorithm or another one to find the minimum cost spanning tree to minimize that edge cost total. All right, so today we're going to the bottom layer that we're going to cover in this class, which is the link layer of networking. Like I've said before, that every layer in networking has a set of protocols or a protocol for solving a different set of problems. We were just talking at length about the network layer. We talked about how to get packets from a source to a destination across many hops. This time we're going to be focusing on a single hop. Okay. We have a physical channel of some kind of medium, some link, one link that some nodes are connected to, and we want to share that with several transmitters and receivers that are all kind of like in one place. Okay, so this is about protocols that are used in one location to deal with neighbors. Okay, that's what the link layer is all about. So transport was about end-to-end, HTTP was about applications end-to-end, network was about getting end-to-end, but the link layer is about dealing with your neighbors. Okay. At this point, since we've gotten to the last layer we're going to cover, although we're going to squeeze in a security layer later, but these are the main layers, the basic layers. It's helpful to review. One way of reviewing this is to think about where each layer is implemented. The HTTP layer, or the application layer in general that we discussed, is implemented in user level applications, or maybe a library that you're using in your application. Like HTTP is available, for example, built into Python as an example, so that might be a language that supports HTTP requests. The transport layer protocols like TCP, those are generally implemented by the operating system. Networking, so that IP addresses and routing and stuff, that's handled by a combination of the operating system on a machine that requests IP addresses and stuff, but also routers. And mainly, most of the work is implemented in routers that implement BGP, and also software-defined networking, which we didn't talk about really. It is another way to handle controlling networking, but I'm not showing that in this picture. The link layer we're talking about today, that those local protocols for handling multiple nearby hosts, those are implemented in a combination of hardware on a single machine. So this big square here, this rectangle, represents a computer, a typical your laptop computer. So a driver or the hardware for your network card would be handling that protocol, And then also all the other devices that connect, that have links, like routers and switches and base stations, also have that same, have to have some kind of link layer protocols to work with the links that they are managing. Okay. I want to cover some terminology first, and then we'll get into link layer protocols. So here's a view of a simplified network that has clients and a router at the core, and a wireless base station for some of the clients, and some of the other clients are connected to switches with a wired connection. So we have cables that are the lines. We have switches. We'll talk about switches in the next class, actually, in detail. We have a base station for wireless hosts to connect to, and we have a router. If I use the term node, I'm talking about either hosts or routers, which is to say, computers or routers, not switches, and not base stations. Links are communication channels that connect adjacent nodes in a communication path. They could be wired, wireless. They could even be LANs, which are collections of wired links, which I'll talk more about in the next lecture. And the final bit of terminology that you should know, and this will maybe become more important in the next lecture, so maybe the slide should have been pushed forward, but anyway. The next bit of terminology is layers of the internet. I showed layers before in the picture, but they're numbered. So the first one you see here is layer 2, and then layer 3, and then layer 4. The first layer I'm not showing, or I don't talk about, is the physical layer. That's just the physical connectivity. So physical connectivity is called layer 1 in the traditional what's called OSI model of networking. But there's no protocols there. That's just physical connections. Layer 2 are the protocols that are needed to manage a physical connection. IP for routing is layer 3, and your transport protocols like TCP are layer 4, and then there are layers above that, like HTTP would be layer 5, and so on. Okay. A point of clarification about routers. Why does a router need to have multiple IP addresses? That's so it can communicate on multiple subnets. Routers route packets between subnets, and there's no one IP address this router can have that would be present on both these subnets, because these subnets don't overlap. Okay, so that's the reason this router has multiple IP addresses. Just kind of a random loose end that we didn't cover before that I wanted to get out of the way. Okay, but now let's move on to the real topic of today, which is medium access control. Okay, sometimes called MAC. So whenever we have communication, it's happening in some kind of physical medium. So medium is a word that refers to that thing the communication is happening over. The plural of that is media. So for example, wireless communication happens in an open space in some frequency band. Wired communication happens on a wire, some kind of wire. Could be a copper wire for an electrical connection, or it could be a optical fiber for fiber optic communication. In general, we can have many nodes connected to that same wire, just like we can have many nodes that are listening in one wireless frequency band, right? So when we look at these communication media, because we can have more than one node connected, when any one of the nodes sends a message, all the other nodes on that medium get the message. And this actually applies to both wired connections, like in this simple picture I'm showing here. We have 5 machines connected to a wired connection. They all would get a message that was sent by any one of them. It's just an electrical signal that they all get. Same thing applies to radio. If one of them sends a signal, the others in the nearby area would receive it. So in that sense, these links are kind of doing a kind of broadcast communication where one node sends and multiple nodes nearby receive. Okay, I mean broadcast on a link, not really broadcast in the same sense of the last lecture. In the last lecture, we were talking about IP broadcast, or like a multi-step broadcast where we propagated stuff along multiple hops. But just locally, it's a kind of broadcast when you have one node that sends a message and multiple neighbors hear it, right? So they're sharing a single channel, and we need some way to handle that sharing, and that's what medium access control is for. And notice this is not necessary if we have point-to-point links that only have two nodes that are connected to each other, and there's a separate send and receive wire. So in other words, I send something and it goes to my neighbor, and my neighbor sends something on a different wire that goes to me, and those are just like single directional links, and I'm the only one that can send on my outbound link, and the inbound link can only receive data from one neighbor. Those kind of point-to-point links don't need any special protocol to manage the sharing of that link, because there is no sharing. Okay, but those are used actually for long distance communication, especially with fiber optic cables. You see fiber optic cables actually have two separate wires. You can, well, not wires, but fibers that you can see. Ethernet cables also are point-to-point links, but when they're connected to a switch, it becomes a broadcast network. We'll see that in the next lecture. Okay. But I think to start off with, let's keep in mind the problem of wireless. Wireless is the easiest example to see where we need to have some kind of sharing protocol for neighbors. Okay. Again, we'll see in the next lecture why this also applies to wired connections. So if we have a wireless connection, multiple neighbors nearby, multiple laptops are trying to communicate through a base station, the problem we have with that sharing is collision. There's a possibility that multiple nodes might try to communicate at the same time, and those simultaneous messages will interfere with each other. They'll kind of overwrite. They'll be transmitted at the same time on the same medium. You won't be able to split them apart because they're kind of being transmitted on the exact same medium, the same communication channel. So both of those messages will be corrupted. They'll be kind of written on top of each other, and neither one can be received. And that's a waste. That's called a collision. Okay, that's bad because time is wasted, bandwidth is wasted, and those messages have to be retransmitted. Okay, when we're doing sharing, there's essentially there's a fundamental trade-off between collisions. If we're doing a lot of sharing, and we're aggressive about sharing, we'll have more collisions. But if we have less, if we're more polite about sharing, then we waste time. So I guess when I say here there's a trade-off in the whatever rules we decide for, whatever protocol we decide for handling collisions. Either if it's aggressive, it might not avoid the collisions that we're trying to avoid. But if it's too conservative, if it's too polite, then it might waste time by not sending during an opportunity. Okay. With these multiple access protocols, we have some simple goals, right? Let's assume we have multiple nodes that are sharing a link that has a throughput of R bits per second at most. Okay. And basically the goals are as follows. If there's one node communicating, it should get the full capacity, that full bandwidth R. But if there are n nodes that have data to send, they should get an even share, a fair share each of R divided by n of the bandwidth. Okay, so that's the first thing, and we'll see that this is actually difficult to achieve precisely, especially with simple protocols. So we want to allow, if there's no sharing, then one node should be able to use the whole capacity. If there is sharing between n nodes, they should evenly split the capacity and not have additional overhead. It would be nice if the protocol was simple and decentralized, so there was not a single point of failure, and inexpensive to implement because of the simplicity. Okay, we'll see later on that there are trade-offs between all three of these in the different styles of protocols for this multiple access. And we'll cover three different basic classes of multiple access protocols: channel partitioning, random access, and taking turns, in that order. Okay, and that'll be the whole lecture actually on covering those with a few examples of each. Okay. Now, channel partitioning is one of the simpler ones, maybe the simplest, because it involves creating virtual channels out of your channel. Okay, and there are three main ways to do that, although I'm going to talk mainly about two of them. The simplest is actually the second one I'm showing here, time division multiplexing. This is where you take, and we talked about both of these actually in the first or second lecture or something like that, but just to review that, you take a channel and you divide it into time slots that recur periodically, which are colored with different colors here, and you just assign different users to different virtual channels, right? So like if you're the blue user, then you have to you can communicate during this blue time. Then otherwise you have to wait, and then then it's green's turn, then it's yellow's turn, and so on. So every user gets 1/4 of the capacity, and there's no collision, right? So we avoided collision entirely because there's no collision because we know exactly when we're supposed to send as long as we know what our assignment is, and no one else will be sending during our assignment because they have their own different assignment. As long as our clocks are synchronized, we can implement this. We each get 1/4 of the bandwidth. That works well if we all need to use the capacity. It's not so great though if the demand fluctuates, right? Like if I need to send a lot of traffic, but my 3 other neighbors are not very busy at the moment, I'm waiting even though they have nothing to send, right? So I'm not achieving that full R capacity for the one node when there's just one node that needs to send. So that's the simplest form where we're doing it based on time. There's another variation of this called frequency division multiplexing, where we take those 4 nodes and if we're using a channel that has like a range of frequencies that the signal can use, we divide the frequency bands among the users, and then the user can send at any time. But when a user does send, it's limited to you sending a signal that falls within that frequency band. So, I mean, technically what this means, it might not make a ton of sense unless you're an electrical engineer or you know a lot about Fourier transforms. But basically, the signal you send has to be composed of sinusoids that are within this frequency range, if you're in the purple, and not this other range. So you're limited in the types of signals you can send, and the information you can send is actually 1/4 now of what you could have sent if you had access to the frequencies that the others are using. Okay. So again, you get 1/4 of the capacity. Why do you get less data throughput when you're assigned one frequency? I feel like I actually just answered that, so I'm going to skip through that. It's because you're only using 1/4 of the frequencies. So your signal is limited to be composed of just sinusoids in 1/4 of the range. I mean, to really understand that, it's a little bit deep, and I'm not going to get into that. I think intuitively at a high level that makes sense. It's easy to accept. Okay, so frequency division multiplexing kind of occurs at the grand scale across the whole radio spectrum, and that's done by the FCC. So the FCC is the Federal Communications Commission in the United States. That's the organization that's responsible for deciding what frequency ranges of radio can be used by different people, different organizations and companies and individuals. And it's really complicated. So they allocate spectrum from like, what is this? 1 kilohertz up to 300 gigahertz. So basically all the usable radio spectrum. And this changes over time as needs change. If we zoom in on, you should actually check it out by clicking the link in the PDF. But I'm going to zoom in on one part of it just to show you an example. So it's very detailed, and the frequencies are divided into really narrow bands sometimes. So, for example, we call frequency ranges bands, by the way. And here's an example of a broadcast television band. So this particular part of the spectrum is used for broadcast television. There actually are many chunks dedicated to broadcast television. See, a lot of these, like this one up here is AM radio. This one down here is broadcast television, more broadcast television. I think FM radio is down here, and more broadcast television over here, and so on. So there, any one particular service is split up. Same thing goes for mobile, like cellular phones. Cellular phone spectrum is split up across a lot of these different purple blocks. Different companies have different frequencies. Yeah, you can see the pink, actually, yeah, pink, not purple. The pink blocks are different kinds of mobile. I'm not sure if all these ones labeled mobile mean mobile cellular phones, but I think they could be. There also are certain bands that are labeled ISM. You can see down here it says ISM. 2.4 gigahertz is one famous one. Another one is 900 megahertz. ISM stands for Industrial, Scientific, and Medical, which, but in practice, what that means is that they're unlicensed and they can be used by any electronic devices that that are limited in their power below a certain amount. I forget exactly what it is, maybe a quarter of a watt. So this 2.4 gigahertz band, this area I'm showing here, even though inside of it you see there are a lot of specific allocations for amateur radio and radio location, and I don't know what these other ones are. Even though they do have allocations for specific purposes, it's also allowed. There are also low power electronic devices are allowed to use those. So microwave ovens, for example, use the 2.4 gigahertz band, I believe. Your Wi-Fi radios, the classic original Wi-Fi is in this 2.4 gigahertz band. Cordless telephones, many of them are 2.4 gigahertz or 900 megahertz. Radio controlled toys like this very nice cat toy could be operating the 2.4 gigahertz band. Because it's unlicensed, any device can use it. The benefit of that is it allows electronics manufacturers to use radio spectrum without having to apply for a reserved chunk of radio spectrum. So it kind of allows innovation in radio consumer devices. But the problem is that there's a lot of collision and there's a lot of traffic in those bands. So if you turn on your microwave, you are going to probably slow down or interrupt your Wi-Fi. If you have a lot of neighbors using Wi-Fi, they're all going to collide with each other, and that's going to slow down your traffic. Okay. That's not true of cellular phones. One of the reasons cellular phones work so well is because they have specific bands that are dedicated. So like a particular company, like let's say Verizon's cellular phones are operating at a frequency that no one else can use. So microwaves don't interfere, and these remote control mice are not competing with Verizon at that particular band. And that's one of the things that allows cellular phones to have such long range. Because there's not a lot of noise, the cell phone can send a signal, and when it reaches the base station that's like maybe a mile away, that signal might be pretty weak, but because there's not a lot of noise from other junk, the base station can still make use of that signal. All right, but that's a kind of frequency division multiplexing across different services. So these are all totally different. Like broadcast TV, of course, is totally different than the remote control mouse. But when I say broadcast frequency division multiplexing is also used for one particular service to distinguish different nodes. And like within television, for example, this is broken up even further into different channels, like different television stations. And when you change channel on your TV, it's moving to a different frequency band. Okay. All right, so these channel partitioning protocols are useful, and they're simple, but there's some downsides. Mainly, it's inflexible, but the way it works is like I said, every node gets a reserved slice of the bandwidth. With FDM, frequency division multiplexing, it's based on a fraction of the spectrum, and thus you get less bandwidth. With time division multiplexing, you get a fraction of the time. You avoid collision. You're fair to the different users, right? You can give an equal amount to different users. You can control that, but it's not flexible. I mentioned that already. By the way, when we use the term bandwidth, I mean, you're probably familiar with you probably used the term bandwidth to refer to throughput, like how fast your internet connection is. That's your bandwidth. But literally, the term bandwidth refers to the width of a frequency band. So it's a size of a frequency range. Like in that picture in the last slide, the width of that rectangle. And it would be technically should be measured in hertz. So today we use it as a synonym for throughput, but the meaning of the term the reason we use the term bandwidth to mean throughput is because the more frequencies you have available, the greater your throughput is going to be. Okay, so we'll use bandwidth interchangeably with throughput, but technically in a radio sense, bandwidth actually refers to the size of your frequency band range, the size of your frequency range that you're using for your communication. And the bigger that is, the more data you can send. All right, yeah, so like I said, these channel partitioning protocols are not flexible because they have a predetermined allocation to every user. Even if just one node wants to communicate, the throughput is limited to your maximum divided by the number of participants, R over N. Okay. And we'll see that we'll introduce some other protocols to fix that. Before I move on, I want to just mention as a side note, code division multiplexing, or CDM, is similar to these two in that it's a channel partitioning protocol, but it's much more difficult to explain and to understand without an electrical engineering background, so I'm not going to explain it. This is actually, though, what's used in a lot of real radio purposes instead of frequency or time division multiplexing. Or sometimes a combination is used, but with code division multiplexing, it's a little bit more robust to noise. What you do is you basically send your signal. Every user has a different code that they use as a carrier, so it's like kind of a signal that is based on a certain different number, I guess, and yeah, your signal is like convolved with that before sending, I think, something like that. So it's a different way of like encoding your signal so that it can be separated from others, but it has the same effect of like giving you a fraction of the bandwidth and being separable on the other side. But it's in practice, it's more robust to noise. Anyway, I want to spend a little bit more time on frequency division multiplexing because it helps us understand some everyday observations we have with Wi-Fi. So Wi-Fi uses frequency division multiplexing to separate different base stations so that we can have multiple Wi-Fi routers, or base stations really is the right term, in the same area. And what I'm showing here is a picture of 2.4 gigahertz Wi-Fi, which is the original Wi-Fi technology or radio. It technically has 14 different channels through frequency division multiplexing, and these like gray slots show the different channels. But the channels overlap. So actually, channel 1 is really the frequencies from 2401 to 2423, and that overlaps with channel 2. So the center frequencies are the gray slots, but they actually each different channel overlaps. So what you really want to do when using Wi-Fi, 2.4 gigahertz Wi-Fi, is only use channels 1, 6, and 11 because they do not interfere with each other. But every once in a while, you might have a badly configured base station that uses a different number. Like, for example, if your neighbor is using channel 9, that's down here, that means that their signal is going to use these frequencies, which overlap with all these other ones here. So in particular, it overlaps with both 6 and 11. So if someone's using 9, then you're stuck. If you want to use something that doesn't overlap, you're stuck using 4, 3, 2, or 1. Or I guess 14, but I don't think 14 is allowed in the US, if I'm not mistaken. So yeah, the fact that they're using a channel that's not aligned with yours was like really unfortunate, because if they had just used let's say channel 11, then you'd have 2 channels free instead of just the 1. Because like I said, you have these 4 to choose from, but any one of them will overlap with the others, so you really just have 1 left to choose from. So yeah, with 2.4 gigahertz Wi-Fi, there are only 3 channels. That means that if you're in an apartment building, you can only have like 2 other neighbors sending data that doesn't collide with you, that doesn't interfere with your traffic. And if you have someone above you, someone below you, someone to the left, someone to the right, that's going to be more than two other base stations. And a lot of times people will make the mistake of having like multiple different base stations and multiple frequencies active at the same time, which just wastes the spectrum. 5 gigahertz Wi-Fi is much better and provides more channels. So if you have the option, especially nowadays, whenever if you're using Zoom or whatever to watch your lectures and do school, and you're having Wi-Fi issues, it could be the problem could be that you're trying to use 2.4 gigahertz in a crowded area. 5 gigahertz offers more channels, so there are 9 channels. This drawing is a little bit different, but you can see these red ones are the 5 gigahertz, the normal 5 gigahertz Wi-Fi channels. There are 9 of them. They're broken into chunks 1 and 6 because they can be used in combination to get higher speed. And if you use all 9 of these red channels, you can get up to 1.3 gigabit per second throughput, which is really pretty fantastic for wireless connection. But that only works if no one else at all is using 5 gigahertz Wi-Fi. And if any one of these channels is used, then that means you have to use fewer channels and get less speed. There also are these other channels in the middle. There are 16 other ones, which are technically dedicated to weather and military radar, but you can use them if the radar is not active at the moment, because these aren't used all the time. So these are called DFS, or dynamic frequency selection channels. And like I said, if you're having Wi-Fi issues, what you can do is do a Wi-Fi scan to see what's happening in your particular area. So let's see. Right now I can go to, like as a demo, go to my Wi-Fi. If you kind of on a Mac, you can option click this thing, then go to wireless diagnostics, and then go to window and scan. And this will show the Wi-Fi base stations in the area. So right now there are 12 that are observed in my apartment. Okay, I just went up to 20. You can see that there are 12 2.4 gigahertz, 8 5 gigahertz. And if you sort by the RSSI, that's the received signal strength. And you can see the strongest one is Candy. That's the one I'm actually using. That's the one in my apartment. And that's using both channel 1 and channel 116. Channel 1 is from the 2.4 gigahertz band. See that? But channel 116 is in the 5 gigahertz band. And I'm using 8 megahertz bandwidth on that. So that's actually, I think, more than one of these 5 gigahertz channels. 116 actually is, you'll see 116 is one of these green DFS channels. So because I'm using a DFS channel, actually most routers don't easily support these DFS channels. And when I say router here, I mean your home base stations, base station router combination, the little like plastic ones. So so this channel I'm using is not typically going to collide with neighbors, because they're typically either in this red area or they're in one of these yellow 2.4 gigahertz channels. Okay, so if I actually go back to this channel, this thing here, no one else in my area is using 116. The only other one close is 153. 153 is way up here, so it's not going to collide with me. All right, so that's Wi-Fi. But so far I was just talking about the frequency choice, the channel selection feature of Wi-Fi. Wi-Fi actually does both frequency division multiplexing, creating multiple channels, but it also has another kind of protocol, which is to share among the different users that are on that same channel. So like all of my devices in my home are on the same frequency. My neighbors are on different frequencies. That's the frequency division multiplexing. But for my devices in my home, my laptop and my tablet, for those to share the one channel that I'm using, they need to have a multiple access protocol for that. And we'll see that there's a kind of random access protocol that they use called CSMA, or something like that. I forget the acronym. We'll see. So random access protocols are different than the channel partitioning protocols I just showed, because they don't have a strict partitioning that is like rigidly defined. They allow individual senders to sometimes use the whole capacity to operate faster. So the way I'm going to start off with a simple random access protocol here. So we allow anyone to send immediately at full bit rate when they can. And if there's a collision, then you wait for a random delay before retransmitting. So you have two hosts that are trying to use the shared channel. They both send, and this is a bad case because they decided to send at the same time. That means there's a collision, and they have to retransmit. They wait a random time and try again. And because of the random delay, one of them sends earlier and gets through, and the other one sends. So the randomization will likely cause the two hosts to retry at different moments in the future. What happens if we use a constant retransmission delay? In other words, if we wait for a constant amount of time before retransmitting, what's the problem? Stop and think about that. Well, I just kind of said it, but we'll end up retrying at the same time if we have a collision and then we The point is that during a collision, we know that two senders were sending at the same time. And if you wait for the same amount of time, that means that, again, the next time you transmit, you're going to send at the same time. So it'll be collision after collision after collision. But one thing I haven't just mentioned here is how to choose the random delay. I also haven't mentioned how you notice that there's a collision. Okay. So the first example I'm going to show of this is called ALOHA, which was an early random access protocol invented in 1970. So this is just like a historical example to give you the basics of random access protocols. And this was actually for radio communication between the Hawaiian Islands, or some of the Hawaiian Islands. And just like I mentioned before, in the simpler example, you would send your data immediately if you had data to send. If there was a collision, you would retransmit the packet. But the way that you determine the delay is that you have these time slots, and in every time slot, you would send with probability p, or wait, with probability p minus 1. And these time slots were determined by the size of the time needed to send one packet. Okay. So you'd have some kind of random number generator, basically. And there's this constant p that weights the likelihood of your deciding to send. And you keep trying until the packet is sent. In other words, you keep trying until you eventually generate a number that is less than p. And in this simple network that I'm describing, this ALOHA research network in Hawaii, there was no collision detection, so you just had transmitters. And actually, the transmitter and receivers that the devices had were on different frequencies. So there was a central node that broadcast things on one channel, and there were two channels. All the three like clients, I guess you could call them, were all sending on one channel, which was shared. That's why they needed a random access protocol. But then the central node would send acknowledgements back and data back on a second channel. Okay. So the receiver would use a checksum to determine whether the received packet was correct. In other words, if there was a collision, like two senders were sending at the same time on that same channel, they would overwrite each other, the checksum would fail, the receiver would drop the packet, and it would not send an acknowledgement. Otherwise, it would send an acknowledgement, and the nodes would retry if no acknowledgement was received. But the amount of time they waited before retrying depended on this probability p, and it was randomized. Because they were sending on different channels that they were receiving, they weren't able to listen before broadcasting. So they just assumed the channel was free and sent, and used the acknowledgement that came back as a signal that the packet was received or not. Okay, and that would be usually the reason it wasn't received would be due to collision, because it's just a one-hop network. There are no routers that are dropping things. So we can do a little analysis on this. This delay probability p is a variable we can change because the number of concurrent senders can vary. So like the more senders we have, the more we need to wait, I guess. If there are only two participants, then there's not much chance of a collision, and there's not much chance of colliding again, so you can retry with higher probability. But if there are like 100 nodes participating in this kind of a protocol, then you might want to wait longer to have a better chance of getting the channel free after a collision. So the book has a little bit of a derivation showing that if the channel is busy, you get 18% of peak throughput on average for all those nodes that are sending, which is not good, right? 18% versus 100%. One way to improve this is what's called slotted ALOHA. This is where you actually have time synchronization between the nodes, which is how I showed it originally. But if we do assume that there's time synchronization, they all start sending at the same time, the retries all happen at the same times, then any one packet that you send that might collide would only collide with one other packet, not two. Like if there's not time synchronization, then this one packet, if it's shifted over, could conflict with both the C and the E time slot instead of just the C. Okay, and by doing that, you get twice as much peak throughput, 37%, but still that 37% is much less than the 100% that we would like to get for even in the busy case. Now, of course, when the system is not busy, then we can send at the full bit rate, and so we get 100% capacity, which is great. It's simple and decentralized, but the cons are that when the system is busy, the throughput's pretty poor. And the basic reason for that is because we're not listening before we're sending. We're just kind of trying and hoping it goes through. Okay. So how would we improve this? Stop and think about that. Especially to improve the throughput when the system is busy, when there are a lot of nodes that want to send data. What can we do that's more clever than just sending without listening? Well, we can listen. And if there's already data being sent by someone else, then we should not bother to send. And this is what CSMA CD does. So this is another kind of random access protocol, but what it adds beyond what ALOHA does is sensing, and two different kinds of sensing. What I mean by that is, so just this acronym stands for Carrier Sense Multiple Access with Collision Detection. These are two different features of it, the carrier sensing and collision detection, but they both relate to listening. With carrier sensing, what that means is that you listen on the channel before you send on the channel. If it's busy, then you wait. And this, of course, prevents a collision. If someone else is sending, then if you were to send, that would definitely create a collision, so you shouldn't do that. Now, in the original ALOHA design, like I said, the participants didn't have the ability to do that, so they didn't, because they were only listening on a different channel, a different frequency, not the frequency they were sending on. But if you could listen, if you're using just one channel for both sending and receiving, then you should be able to listen and do this carrier sensing where you listen before you send. Another and more difficult thing to do is collision detection on the sender side. So while you're transmitting your packet, your data, you listen to the data you're sending. Like you listen to that same channel. What you should see is exactly the data, just a copy of the data that you think you're sending. So you're energizing the channel with a certain signal. What you should observe on that signal is the signal that you're sending. If you notice, if instead you sense your signal plus some other noise, which is probably someone else's signal, that is a collision, and you should stop sending. The benefit of stopping at that time is that you minimize the channel time that's wasted. If you were to just continue and finish sending your message, that all would be wasted. Okay. So in order to do these things, you need hardware that can detect signals on the transmission channel that you're sending. This is in fact used by wired Ethernet very effectively, and also for wireless Ethernet, for Wi-Fi, less effectively. I mean, the carrier sensing works well for Wi-Fi, but collision detection doesn't work so great on Wi-Fi. Actually, you can stop and think about that. Why might a wireless communication channel be more difficult to do collision detection on compared to a wired channel? This is a little bit tricky, but I'll actually answer this later on. So, yeah, you might think actually that collisions could be avoided using the CSMA CD. Like actually, the fact that we're doing carrier sensing might seem like enough to avoid collisions. Like if the channel is not busy and then you should be able then why would there be a collision when you started to send? Like why do we need the second thing, collision detection, where we're checking for a collision afterwards? If everyone is waiting, if everyone is checking for an idle channel before sending, why is it that we also need to check for a collision after we start sending? That seems unnecessary, right? Well, the reason for that is propagation delay and sensing delay. So in an ideal world, yes, you could just check the channel and everyone would check the channel first and then they would send and it would be free and there would be no collisions. But because of propagation delay, your observations of the channel are actually out of date. It could be that you sense the channel and someone else senses the channel, and someone else has started sending a little while ago, but their signal had not reached you yet. That's the propagation delay. And you sense the channel and you notice it's free and you start sending, but it's not really free because someone else started sending a while ago. It's just that signal didn't get to you yet. Okay. There's also a problem in the small delay between sensing and transmission, right? Like you sense the channel, you see it's free, and then you start sending. But that delay before you start sending, during that time, someone else could have, like if two people sense at the same time, they see it's free. Even if there's no propagation delay, they could see it's free and then start sending at the same time, and there'd be a collision. Right? So for both of those delays, the propagation delay and the sensing to transmission delay, make collisions possible. So this illustration shows that. We have 4 nodes here that are connected with, let's say, a wire, and they're spatially laid out like this. So physically they're separated just as shown. If one of them starts sending, the second one, time is going downward. As time goes by, the slope here of this line indicates the propagation delay. So when I send a signal here, when I energize this link, it gets transmitted. The energy, that signal, whether if it's an electrical signal, maybe it's the voltage, rises across the wire in a gradual way. There's a propagation delay. So eventually it reaches these 2 neighbors on the side, 1 and 3. But at that time, still it has not reached the 4th node. And if that 4th node had sensed the channel a little while ago, well after, this time it did the sensing actually was significantly after when the first node started sending, but still the signal had not gotten there yet to the 4th node. So it starts sending at that time, and it thinks everything is fine, except there does end up being a collision because of that propagation delay. And then this checkered area is the time, the places both in time and space when the 2 signals overlap with each other. Okay. And that causes corruption. Okay. So collision detection is, now we're assuming we have carrier sensing. That is, we don't send if the channel is busy, but that wasn't enough. What we're adding now is collision detection to minimize the impact of propagation delay, to minimize the inefficiency that's introduced by these collisions that happen due to propagation delay and other delays. So we want to detect collisions and stop transmitting. So the way we do this is we measure the channel while we're sending, and if the energy is greater than the transmitted energy, like if I'm sending a 1, and let's say that means that I set the voltage to level 1, just to simplify it, 1 volt. If I notice that the voltage is 1.1 instead of 1, or it's 2 instead of 1, let's say, that means maybe someone else is also charging the wire at the same time. That's just bad simplification of how electricity works, but hopefully you get the idea. So if we're doing collision detection in this scenario, we have the second node sends data, the yellow data. Eventually, it's actually sensing the whole time, so it's checking the channel to see that the energy is matching its own signal. And so far, everything it sees is normal. But eventually, once it gets to this checkered time, when it's doing this collision detection sensing, it notices that the signal on the link is actually higher than expected, because the energy from the second transmitter, this red signal, is being added on top of my own, and that leads to a detection of a collision. So there's a little bit of a delay because it needs to be sure, like it maybe waits a little while to make sure that the energy is consistently above what it expects. But once it's confident, it actually stops transmitting. So this yellow packet was not finished. It actually would have gone maybe twice as long, but it stopped early because it noticed something weird on the channel. In other words, it noticed the collision. And the other sender would also do the same thing. Okay, it would send for a while the red packet. Eventually it notices that there is more energy in a channel than it expects, given the fact that it is sending. That tells it that there actually are 2 people sending, and so it stops. Okay, now notice that on a wired link, maybe the energy difference would be high, but on a wireless link, it would be more difficult to detect that signal. Because on a wireless link, the received radio signal is going to be very weak compared to your own. So radio kind of spreads out and decays because it has to geometrically grow and cover a wider area. So whereas a wired link is directional, is contained in a wire. So the signal that you receive here, like this red signal, when it reaches this second node here, the red signal will be pretty strong if it's wired, but if it's wireless, then your own signal is going to be a lot stronger than your neighbor's signal, because you're sending it here, like your wireless signal is concentrated here at your antenna. You send it out and it gets weaker and weaker very quickly because it spreads out instead of just traveling along a single direction like a wire does. So this is why I say that Wi-Fi technically does collision detection, but it doesn't use it as effectively as wired Ethernet does. So that was the answer to the question I posed earlier. Okay, so to break this down into steps, we have carrier sensing first. First, we listen to the channel before we send. If the channel is busy, then we wait. If not, or once it becomes free, we start sending our data. While sending data, we do collision detection, which means we listen to the channel while we're transmitting. We're not listening for data, but we're listening to see whether another transmission is being sent on top of ours, like if we see something different than just the data we're sending. And you can, depending on the medium, you might do that based on the energy level or something else. I don't know. It kind of varies. But just abstractly, we check to see whether there's an additional transmission happening at the same time. Now, if there is a collision, I said before that you stop. Now you stop, but then you have to retransmit, right? The rule in CSMA CD is to retransmit with a random delay, but that random delay uses a binary exponential backoff. So initially we have a random delay between 0 and some constant c, but then it goes up exponentially if you keep having collisions on that same packet. Okay, so using this formula, c times 2 to the n minus 1. And so for Ethernet, there's a certain, c is set to a constant that depends on the bit rate of the link, and this exponential growth is limited. After n rounds, it stops growing exponentially. And notice that this exponential growth is just for each packet. Once you send that packet, once it gets through, then you restart it. So the next time there's a collision, you start back with the small random delays. So they're randomized, but they have exponential growth in the the constant for that, in what the range of the random numbers are drawn from. Okay, so moving on to another type of protocol, the third type. So the third type is taking turns, and this actually tries to combine the benefits of the previous two that we just had. So the second type of protocol is the random access protocols, like what I was just talking about with either ALOHA or CSMA CD. Those don't have a guaranteed fair share of bandwidth, right? Because users just try to send randomly. But the benefit there was that if there's only one user that needs to send, they can send a lot of data. What taking turns protocols do are get the benefit of time division multiplexing, which was that there were never any collisions. Time slots were reserved, but reservations are dynamic and they're not pre-scheduled. So it's kind of like time division multiplexing, but with a schedule that changes over time to match the demands of how much data needs to be sent by the different users, different hosts. Okay. Bluetooth is an example of a protocol that uses time division, that uses taking turns, a taking turns protocol. It also uses frequency division multiplexing at the same time. We'll see in practice a lot of wireless communication, for example, uses a combination of different media access control protocols, and even some wired communication uses a combination of different protocols. Both, And next lecture, I'll have a good example of that for cable modems. Okay, so Bluetooth uses taking turns protocol. Specifically, it's a polling protocol. This is one type of taking turns protocol. So this involves one node being the leader. So if we're talking about Bluetooth, that might be like your computer is the leader, and all the devices like your mouse and your headset, those are the like listeners or followers, let's say. And what the leader does is it's responsible for deciding who is allowed to send at what time. in doing this like scheduling of the time slots. So the leader goes around and polls the nodes in a round robin manner, telling them that they can send up to H packets. Okay, so this picture on the bottom shows that. So the orange packets are messages sent by the leader to everyone. Remember, this is a broadcast medium where there are like there's A, there's B, and there's C, and there's the leader. So there's a leader, there's A, there's B, and there's C. So there's actually 4 different participants. So the leader, first the leader polls A, and that means that A can start sending. So everyone gets this message, but A in particular uses that as a signal to send some packets that it has ready to go. When those 5 packets are done, the leader notices, right? The leader's been paying attention. The leader now polls the next participant, which is B. B now has the ability to send 5 packets. It chooses to send 1 packet. Maybe it's just like a keyboard or something that doesn't have a lot of data to send. It just has a little bit of data. So it sends that 1 packet. The leader sees that there's silence. So B must be done. So then the leader polls the next device, C. That C device has no data to send, so it doesn't do anything. The leader notices that, and then it pulls A again. So it goes around in a circle. Now A is the device that has a lot of data to send, so A will send as much data as it can, and then it continues to pull B and C and so forth. Okay. So the nice thing about this is that there's never any collisions. At any given time, everyone knows whose turn it is, but the allocation of time is flexible in the sense that if someone doesn't use their reservation, like B only used a little bit of their time and C did not use any of their time, then the leader comes in and moves along to the next user. Okay, and it also limits any one user. If everyone wanted to send out once, everyone has this maximum of 5 packets they can send, so the data would be evenly split among the bandwidth would be evenly split among the 3 participants if they all had data to send. The only downside, though, is we've added some coordination overhead. So these orange packets are taking up time when no useful data is being transmitted. It's just coordination, like it's just telling someone else to send. But this is not drawn to scale. I had to just draw it this big so I could fit all the letters in. You can imagine that the overhead, these orange slivers could be pretty short compared to the data. Okay, so actually this is a pretty good design. And like I said, it's used by Bluetooth. Another variation of a taking turns protocol is a token passing protocol. This is similar to a polling protocol, but there's no special leader node. Instead, people take turns being the leader, sort of. So the nodes have a designated order, and each node transmits up to some maximum amount of packets and then sends a special message, which is the token, to the next node, telling that next node it's their turn. Okay, so only the nodes holding the special packet can send. Only the nodes holding the most recently received the token can send packets, and it passes it on. So collisions are always avoided. Like only one node is elected at any time to send packets. Elected is the wrong word, but it's chosen. The benefit of this versus the previous one was there's no central leader. It's kind of more equal. But in both this case and in the previous case, if a node fails, that could bring down the whole system. In the previous case with taking turns, if the leader fails, that's a big problem, right? Like B will never. Like keep in mind in this design, A and B could be the machines communicating. Like they're not all necessarily communicating with the leader, but the leader is responsible for saying who can talk when. Like these packets that A is sending, those might be received by B, and this purple packet might be an acknowledgement from B going back to A, as an example, or they could be going to the leader. Who knows? But the point is, if the leader fails, then the system stops making progress. Same thing here, not with a leader, but if the node that's currently holding the token fails, then no further progress will be made because the token will not be handed off to someone else. Okay. So to summarize these protocols, there are 3 different classes: channel partitioning, random access, and taking turns. For each one of those 3, I gave 2 different examples. And they have different trade-offs in terms of the single sender throughput. This is how much data can be sent if there's only one person who wants to send. That is the best. That's best for the random access protocols. It's the worst for channel partitioning. Taking turns is a trade-off, but the trade-off that where taking turns has an advantage is in the busy throughput. So compared to random access. So when in the random access protocol, when the system is busy, with ALOHA, we had really bad performance because there was no sensing. With CSMA CD, the performance could actually approach the optimal if the propagation delay and the is low. But if there is propagation delay, this is going to be generally less than the maximum. But then for taking turns, you have the overhead, the minus C times N is for the coordination. Okay. We also, so in the random access ones, we have collisions that are possible. Some of these are centralized, some are not. Some are sensitive to crashes, some are not. Some require time synchronization, and some require carrier sensing. Okay. So to recap the whole lecture, these link layer protocols are needed to handle the sharing of a physical link, or which we call a medium, with multiple nodes that are trying to communicate on that. So this is for handling your immediate neighbors. We call it medium access control or multiple access protocols. So two different M acronyms, MAC or MAP. These decide how to share a link. Two nodes that try to send data simultaneously causes a collision and the packets are lost. And fundamentally, these protocols are about handling collisions, whether by preventing them entirely or having some way to deal with them when they happen. Okay, we talked about the three different classes of sharing protocols and the two examples within them. Just to point out, I want to point out that Wi-Fi uses frequency division multiplexing for the different channels that are available for different base stations, but also CSMA CD for handling the packets that are sent within a single channel. So the sharing between your laptop and your tablet, for example, is doing CSMA CD. And Ethernet also uses CSMA CD. Bluetooth uses taking turns, though, instead. Okay. So next time we'll talk more about this stuff to connect it to especially wired networks that use Ethernet.